Hello, welcome to another module in this massive open online course on the principles of CDMA, MIMO, OFDM wireless communication systems. And in the previous module, we had seen that as the number of receive antennas increases in a wireless communication system, the bit error rate decreases significantly. In this module, let us try to understand the intuitive reason behind why this is happening. That is, why is the bit error rate decreasing with increasing number of receive antennas or with increasing receive diversity. So, we had seen, so we are trying to understand bit error rate is the reason why bit error rate is decreasing or the bit error rate decreases with the bit error rate decreases with the number of receive antennas. For instance, for L antennas, let me remind you the bit error rate, approximate bit error rate equals 2L minus 1 choose L 1 over 2 times SNR raised to the power of L. Therefore, if L equal to 1, for L equal to 1, this bit error rate equals, or rather the approximate bit error rate equals 2L minus 1, that is 1 choose 2L minus 1 choose L, that is 1 choose 1 over 2 SNR raised to the power of 1, which is basically equal to 1 over 2 times SNR, which is indeed proportional to 1 over SNR as we had seen before. That is, with for L equal to 1 antenna, the bit error rate is approximately 1 over 2 times SNR, which is decreasing as 1 over SNR, and this is a very slow decrease of the bit error rate with respect to SNR as we had seen earlier. Now, what happens with L equal to 2 antennas? For L equal to 2, and this also we have seen earlier, my bit error rate equals 3 choose 2 times 1 over 2 square times 1 over SNR square, which is equal to 3 by 4 times 1 over SNR square, which is proportional to, as you can see, 1 over SNR square. So, for L equal to 2 antennas, the bit error rate is decreasing as 1 over SNR square. And now, let us see what happens with L equal to 3 antennas. For L equal to 3 antennas, our bit error rate is equal to 2L minus 1, that is 5 choose L, which is 3 1 over 2 SNR raised to the power of 3, which is equal to 5 factorial divided by 3 factorial times 2 factorial times 1 divided by 8 times 1 over SNR cube, which if you simplify can be seen to reduce to 5 over 4 times 1 over SNR cube, and therefore, the bit error rate decrease is proportional to 1 over SNR cube. So, for L equal to 1, we have seen that the bit error rate is decreasing as 1 over SNR. For L equal to 2, the bit error rate is decreasing as 1 over SNR square. For L equal to 3, the bit error rate is decreasing as 1 over SNR cube. And therefore, we can see that as the number of receive antennas is increasing, the bit error rate is decreasing faster and faster. In particular or in general, for L, that is with L antennas, our bit error rate decrease is proportional to 1 over SNR raised to the power of L, and therefore, as L is increasing, the bit error rate is decreasing faster and faster. With 2 antennas it is 1 over SNR square, with 3 antennas it is 1 over SNR cube, and as L increases, the bit error rate is decreasing at a much faster rate. And therefore, we want to understand why is this arising. Reason why is this? Or in other words, what is the reason behind this increasing rate of bit error rate decrease, or what is the reason behind this faster decrease of bit error rate at increasing number of receive antennas. And to do this, we would like to use a deep fade analysis. So, we would like to look at a deep fade analysis similar to the single antenna scenario. Deep fade analysis for we would like to look at a scenario of deep fade for a multiple antenna system, and we have seen that in a multiple antenna system my received signal is y bar equals h bar x plus n bar, that is the signal y bar, that is if I have L antennas, let me remind you, I have y1, y2, yl, equals h1, h2, hl times x plus y bar equals h bar x plus n bar, right. And at the receiver we perform maximal ratio combining for this L antenna system, where h1, h2, hl are the channel coefficients, and after maximal ratio combining, that is after MRC, the SNR after maximal the SNR after maximal ratio combining is, remember we have SNR equals P times norm h bar square divided by sigma square. Now, what we also did is we denoted this norm h square as G. So, let us use G equals norm h bar square, then I can write this SNR as G times P divided by sigma square. So, SNR equals SNR after MRC in this multiple antenna system equals G times P divided by sigma square. So, one can think of this as the received power equals G times P, and the transmit power or the noise power equals to sigma square. And we already said that the system is in a deep fade. Remember, we defined the deep fade event as the scenario when the received signal power, the level of the received power is lower than the noise threshold, therefore, the signal cannot be distinguished from noise. Therefore, the deep fade occurs when the received power, that is Gp, is less than the noise threshold, that is sigma square. So, our deep fade occurs when received power is less than noise power, which basically implies that the received power Gp is less than the noise power sigma square, which implies G is less than sigma square by P, but remember sigma square by P equals 1 over SNR, since SNR is P divided by sigma square. So, we say that the deep fade, that is deep fade occurs, that is condition for deep fade is G less than So, our condition for deep fade, this is our condition So, our condition for deep fade is that the gain G is less than 1 over SNR. This is the condition for the deep fade. So, now the probability of deep fade is that the probability. So, the probability of deep fade is simply the probability that this gain G is less than 1 over SNR. Remember, this G equals norm of h bar square. So, we are saying the probability of a deep fade is simply the probability that this effective gain G equal to norm h bar square, norm square of the channel vector, is less than 1 over SNR, right. And now, we have also seen that this G is a chi-square random variable. This is a chi-square probability, this has a chi-square random variable with 2L chi-square random variable with 2L degrees of freedom, and the probability density function, the PDF or the probability density function and the PDF or the probability density function is given as f of G equals G raised to L minus 1 divided by L minus 1 factorial into e raised to the power of minus G. So, we had seen that the probability density function of this gain G is a chi-square random variable, which is given as G raised to L minus 1 divided by L minus 1 factorial times e raised to minus G. And therefore, now the probability that G is less than 1 over SNR, the probability that G is less than 1 over SNR can now be obtained by integrating the probability density function of G between the limit 0 to 1 over SNR So, the probability that G is less than 1 over SNR, which is the condition for the deep fade, remember this is the condition this is the condition for deep fade. The probability of deep fade is basically the probability that G is less than 1 over SNR, which can be obtained by integrating the probability density function of this gain G between the limits 0 to 1 over SNR, and that is given as the integral 0 to 1 over SNR times G raised to L minus 1 divided by L minus 1 factorial e raised to minus G dG, correct, and therefore I am integrating the probability density function of G between the limit 0 to 1 over SNR, and now you can see at high SNR, now you can see that at high SNR which means SNR is tending to infinity, 1 over SNR is approximately 0. 1 over SNR is approximately 0, which means I can say that G, that is we are considering limits between 0, remember we are considering G 0 less than equal to G less than or equal to 1 over SNR, that is G is between 0 and 1 over SNR, and 1 over SNR itself is very close to 0, which means G is very small, the quantity G is very small, which means e to the power of minus G is approximately equal to 1. Therefore, since 1 over SNR is small, G is between the limit 0 and 1 over SNR, and therefore e to the power of minus G is approximately equal to 1, and therefore my G to the power of L minus 1 divided by L minus 1 factorial e to the power of minus G is simply equal to, is approximately equal to G to the power of L minus 1 divided by L minus 1 factorial. Therefore, probability of deep fade, that is the probability of deep fade is simply (0 to 1 over SNR G to the power of L minus 1 divided by L minus 1 factorial times dG, since e to the power of minus G is approximately equal to 1. This is further equal to, now I can evaluate this integral. So, this is 1 over L minus 1 factorial times G, integral of G to the power of L minus 1 is, remember this is G to the power of L divided by L and evaluated between the limits 0 to 1 over SNR, and now you can see 1 over L minus 1 factorial times L is 1 over L factorial. G to the power of L evaluated between the limits 1 over SNR and 0 is simply 1 over SNR raised to the power of L. So, therefore, this is 1 over L factorial 1 over SNR raised to the power of L. So, probability of deep fade which I can also denote by PDF equals 1 over L factorial times 1 over SNR raised to the power of L, which you can see is proportional to 1 over SNR raised to the power of L. So, what you are seeing here is something very interesting, that the probability of deep fade is now proportional to 1 over SNR raised to the power of L, where L is the number of receive antennas. So, where L, this L is the number of the probability of deep fade is now proportional to 1 over SNR raised to the power of L, where L is the number of receive antennas, and hence naturally the probability of deep fade, which was earlier 1 over SNR, remember for a system with a single receive antenna it was 1 over SNR, with L receive antennas this probability of deep fade has become much smaller, it has become 1 over SNR raised to the power of L, and therefore as the probability that the system is in a deep fade has decreased, as a result of it naturally the bit error rate which is arising because of the bit errors which are arising for this, which are arising out of these deep fade events have also decreased, and hence the bit error rate has decreased because the probability of bit deep fade is has decreased to 1 over SNR raised to the power of L, and this is a key result. Let me write it down again. This is the probability of deep fade is proportional to 1 over SNR raised to the power of L. So, what we are seeing is with increasing number of antennas L, the probability of deep fade decreases, and this leads to a significant decrease in the bit error rate. So, what we are seeing is that the reason for this significant decrease in the bit error rate with increasing diversity or with increasing number of receive antennas can be attributed to the decreasing probability of the deep fade event. We have seen that the probability of deep fade is now proportional to 1 over SNR raised to the power of L. Therefore, as L is increasing, the probability of a deep fade is decreasing, and hence naturally the resultant bit error rate is also decreasing, because earlier we said that it is the deep fade events that lead to the high bit error rate of a wireless communication system, and naturally as the probability of deep fade is decreasing, the bit error rate is also decreasing. And this is a very interesting aspect of wireless communication systems with diversity. So, we will stop this module here, and what we have done in this module is that we have gone through a deep fade analysis for a wireless communication system with multiple, that is L receive antennas. And now what is the reason for this decreasing probability of deep fade? What is the intuitive reason behind this that we are going to look at or explore in the next module. So, this module let us stop over here. Thank you very much.